So we are still learning about carbonyl chemistry. It's a long chapter, but we are learning a lot. Don't you feel so? Okay, so now we're going to learn another new reaction that the carbonyl compounds undergo. That is called Wittig reaction. It has a very nice way of making an alkene from a carbonyl compound. And in organic synthesis, we use this very often. Okay, it has a very versatility in synthesis of new molecules. Then you will see why. And here we start with a carbonyl compound. Of course, it's going to be aldehyde or a ketone. And this is going to be reacted with a compound containing phosphorus. We call it as a phosphonium yelide. Okay, yelide, there is a definition for the yelide in the next slide. I'll explain it to you there. But we're going to be forming a compound by mixing a few other reagents. We form this compound, and once this is being formed, these two groups where you have a carbon, this carbonyl group, oxygen is going to exchange to this group right there. Okay, these two are going to connect. Carbon going to connect to the double bond to this carbon, forming an alkene, and then the groups on the carbon will retain in the alkene. And this group right here, phosphorus with the three phenyl groups, will become triphenyl phosphine oxide. And this is like the summary of the Wittig reaction. And let's look at this now in a little bit more detail. So phosphonium yelide. So the phosphonium yelide, what you have seen in the previous slide is this group. Okay, phosphorus has three phenyl groups, and if you expand this structure, it would look like this. Phosphorus, where can I write? Okay, let's write it over here. Phosphorus has three phenyl groups. You guys know what is a phenyl group? It's a benzene ring, right? Phenyl. There are three phenyl groups like that, and then phosphorus is double bonded to the carbon, and then this carbon can have any substituents of interest. Okay, so this is the phosphonium yelide, and similarly the double bond can be opened up and have a resonance structure like this. If the pi bond gives its electrons to the carbon, it would look like that. So like this. Phosphorus going to be positively charged and carbon going to be negatively charged. So meaning, so this is your phosphorus, carbon have hydrogen, your alkyl group. Now you gave 2 electrons to carbon, and then the phosphorus will have its 3 phenyl groups. And let's look at the formal charges. Now the carbon is in group number 4. Remember how to calculate the formal charge, group number 4, and then you subtract the number of bonds and the lone electrons on carbon. So 3 bonds, 2, lone electrons 5, 4 minus 5, it will become -1 charge. And then the phosphorus, group number, what's the group number for phosphorus? 5, right? So 5 minus a number of bonds, 4, there are no lone electrons, so 5 minus 4 plus 1. Okay, so the carbon is going to be -1 like here, and then phosphorus would be +1. So phosphonium yelide. So this phosphonium yelide, we can see that the carbon is negatively charged, meaning carbon can now act as a nucleophile. Okay? Okay, and a yelide. And you had seen in the structure that we had drawn before, a yelide is a species with opposite charges on adjacent atoms with complete octets. So carbon has a complete octet, 8 electrons, 3 bonds and 2 electrons. And then phosphorus also has a complete octet, 3 bonds to phenyl and a 1 bond to carbon, 4. 4 bonds, 4 times 2, 8 electrons, complete octets. But they have opposite charges. Okay? But how do we synthesize this phosphonium yelide? What are the things that we're going to use? It depends on the what substituents we want in our final alkene. we always start to making the yelid with triphenylphosphine. Triphenyl, phosphorus with 3 phenyl groups. So phosphorus is now carrying 2 electrons, and it's going to react with the alkyl halide as a SN2 reaction. SN2. Yes, SN2, that's correct. Yeah, SN2. So triphenylphosphine, primary halide. Since the lone pair coming from the phosphorus, that's going to be your nucleophile, comes and attack the primary carbon, and you leave the bromide. Okay, so the new carbon phosphorus bond is being formed, carbon with the phosphorus. And then the CH2, CH3. So here you have 2 hydrogens on this carbon. Phosphorus is positively charged, but carbon is not negatively charged yet. Okay, there are 2 hydrogens here. So then you use another base, N-butyl lithium, N-bully. We normally call it as N-bully. N-butyl lithium, N-bully. Okay, so N-butyl lithium going to act as a base, and then there are 2 hydrogens here, and I'm going to put 1 hydrogen there, and then this is going to go and grab the hydrogen and form a negative charge right there. Do you see that negative carbon? So that's how you form the yelid. Okay, a phosphonium yelid. Now when you are choosing which phosphonium yelid you want, you can choose depending on, you can choose the alkyl halide that you want the phosphonium yelid to form. It doesn't have to be ethyl bromide, it could be a different halide also. And that will end up being on the carbon in the yelid. Okay. So once the yelid is being formed, then this is going to react with your carbonyl compound in this fashion. So this is the carbonyl compound, and this is our yelid. Carbon is the negatively charged, phosphorus is the positive charged one. So the carbon with its electrons going to attack the electropositive carbonyl carbon. Once it's been attacked, so the pi bond over here going to form a bond with the phosphorus, because the phosphorus is electron deficient. So pi bond carrying electrons going to form a bond between this oxygen and phosphorus. So you form a 4-membered ring. 4-membered ring forms in the vicinity of positive negative charges. Once it's formed, it become unstable because it's 90 degrees bond angle, and it would become sterically not stable. Okay, it's gonna break down. When it breaks down, it forms the most strongest bonds that it could form. Phosphorus oxygen makes a very strong bond, and again here you can form a carbon-carbon double bond. Okay, so the bond between phosphorus and carbon breaks, gives its electrons to form a double bond between the carbon-carbon, and then the bond between carbon and oxygen breaks and give its electron to form a double bond with the phosphorus. So you form this phosphine oxide, and then the alkene, you just form the alkene you want. So these 2 alkyl groups come from the starting aldehyde or the ketone. In this case it's ketone. And then the other carbon substituents would be whichever you started to form your yelid. Okay, that's how the Wittig reaction works. Synthetic utility of the Wittig reaction. Let's see, you want to form this alkene. Okay, let's look at what are the possible ways that we can make the alkene. We can make this alkene by using the cyclohexanone and then the phosphonium yelid having carbon group as CH2. So when this get together, so this CH2 gonna go to this carbon forming a double bond. And this reaction, there are no side reactions, and you will get most of the product as the product you want, which is this one. And some other ways that we can make this alkene, you can start with the 1-bromo 1-methyl cyclohexane, and you can add a base. So the base would deprotonate. Okay, base would so the base would kick this bromide out, and then again you can form the alkene. And once the alkene is being formed, you will realize that this is the more substituted alkene, which is going to be in the major product, and this would be minor. But what you want is this. See, it's difficult to make this one. And then another way that we can reach to make this compound is by reacting this compound with hydroxide ion. Then we know, so the hydrogen is right there, we can only form one alkene. You cannot form the substituted alkenes with the ring. But that is again going to be the minor product, and instead of forming the alkene, the substitution can take place. Hydroxide will remove bromide group. Okay, so you see, if you try to achieve the alkene from the other methods, the yield is going to be low. But if you do it with the Wittig reagent, we know we can get it in major yield. Okay, that is a synthetic utility of the Wittig reaction. Now, when we are choosing reagents for the Wittig reaction, we need to look at the steric hindrance. Okay, now let's see, we want to make this alkene, and then we can see that if you break the carbon-carbon double bond from there, what are the two pieces that we can get? Remember, for the alkene, the Wittig reagent reactants would be, one side would be your carbonyl compound, the other side is going to be phosphonium yelide. So if you break the bond between carbon-carbon in your mind, this is how it's going to come. One side you can put the oxygen. You see, you put the oxygen into the one side, CH2CH3, CH2CH3, carbon, oxygen. And then the other side you have this part and then the carbon, double bond. Also, we can consider that the carbonyl group come from this side. If that is the case, this is the carbonyl group, and this side come from the Wittig yelide, phosphonium yelide, which is this one. Now we have two sets of reagents, either this carbonyl compound and the phosphonium yelide, or this carbonyl compound and the phosphonium yelide. So how do you pick which one we need to use? The yelide should come from the least sterically hindered alkyl halide. Which one is the least sterically hindered alkyl halide? Remember, this part come from the alkyl halide. Right? Remember, phosphorus is going to attack the carbon and then loses the halogen. So this part comes from the halide. This part also comes from the halide. And we look at here, and we saw when the triphenylphosphine react with the alkyl halide, it's a SN2 reaction. So the less sterically hindered is your alkyl halide would be more reacting. Okay, SN2 would be favored. So we choose the one that can form least sterically hindered phosphonium yelide. That comes from the least sterically hindered alkyl halide, which is this one compared to this. Okay, this would be a secondary alkyl halide, and this is a primary alkyl halide. Okay, retrosynthetic analysis. Now, what is retrosynthetic analysis? Now, a synthesis meaning we add reagents together, and then we put solvents and any other catalysts, and then we get the product. Now the reverse is called retrosynthesis, going back. That's how chemists look at when they want to synthesize a new molecule. They always go backwards. They have the molecule of interest in front of them, and then they do some disconnections and see which connections can be made from the known chemicals and known reagents. Okay. So that is a retrosynthetic analysis. So in retrosynthetic analysis, we have the target molecule and we give this arrow for the retrosynthesis. Normally a forward reaction would be given with this arrow, but for the retrosynthesis you have this kind of open arrow. Target molecule that can be coming from a Y molecule. We can obtain Y from the X. X can be obtained from the W. W will lead to the starting material. and then we need to know how to go forward. Okay, let's see, we want to synthesize this molecule, cyclohexanol. How can we make it? And then we're going to look at, okay, now we're going to do some disconnections. You're going to break the carbon-hydrogen bond. If you break the carbon-hydrogen bond, there will be two charges. So you can put positive here and then the negative there, meaning we call them as synthons, like synthetic equivalents. So they are not existing by itself, but they are in mind, we generate these ions. So we can add a hydride if the site is a positive charge, right? And then how do you create the positive charge here? By having a carbonyl compound. We know in a carbonyl compound, carbon is electropositive, oxygen electronegative. And then we know we can get the hydride from a reducing agent like sodium borohydride. Okay, so then we know the forward reaction is going to be, you start with cyclohexanone, add sodium borohydride, and the second step adding hydronium ion, we can get the alcohol. It is a very simple retrosynthetic analysis, one step. And not only one step, like in this here, there are going to be few more steps, a lot of steps. Okay, if the more complex and bigger the molecule, there are going to be many steps of retrosynthetic analysis as well as for the forward reaction. Here's another one. The same molecule, try a different disconnection. Now you have this alcohol, cyclohexanol. Let's say you break the bond, in your mind you break this bond right there. So then we can consider OH coming as a negative charge, and then here you have a positive charge. So positive negative can form a bond, and then we need to know how can we make this carbon a positive ion. Well, we can make it a bromocyclohexane. Okay, bromine is partially negative and this carbon will become partially positive. So when a hydroxide, a base is added, it attacks to this carbon and leave bromide. Okay, and that would be cyclohexanol. And not only that, you can also get the elimination product, bromine, and then you have, I should not put that there. And here you have a hydrogen. So the hydroxide goes and grab this hydrogen, give its electrons to form a double bond and elimination, E2. So you can form the alkene. Okay, so that's another way. But in this second case, we can also get the alcohol, not the target molecule we want. So those things can happen. Another one. Now we want to synthesize this molecule here, 1-methyl cyclohexanol. How can we make it? Now let's see how to do the disconnection. If you break the carbon-carbon bond right there, you can consider methyl can come as a methine, CH3 minus, and then this on the carbon would be positive. Now how can we create this CH3 minus? We know a method that we can make the carbon nucleophilic. That is by creating a Grignard reagent. Remember, the metal going to be positive, so the carbon will be negative. And then we can make this part a positive by having a carbonyl compound like this. Start with the cyclohexanone and then you react it with methyl magnesium bromide Grignard reagent. Methyl group is a nucleophile, attack the carbon and then form the O minus, and then when you add the water, hydronium ion, it will become alcohol. One step. Okay. And not all disconnections are useful because they do not yield reasonable synthons. For example, if you try to break the carbon-carbon bond of the ring, so you'll have a plus and a minus. So, and also you can break something in the ring somewhere here, plus minus. So no readily available synthetic equivalents. So it has to be something that we can synthesize from the knowledge that we know by gaining the knowledge by doing all these reactions and then getting familiar with the different types of organic reactions. So that is the reason we are learning all kinds of different ways of making molecules. Okay, let's talk about the alpha beta unsaturated aldehydes and ketones in the next session. We'll stop here.